Got it? Okay. So let's talk about that SPEC 20 lab. And you're not going to really have to know like the specifics and how it works. I am going to ask you some questions on it on the lab tomorrow, or on the test tomorrow, but it's just going to be pretty broad and general. So here's the basic idea. You took that cuvette, you shone a light through it, okay? So what I did, I took what's called a water blank, which is a technical name for a test tube filled with water. And I set it up where that light's going to come through there. And over here I said, and there's a sensor, and it picks up how much of this light makes it through. So the first thing I did is I set it up where if this is just pure water, I get 100% transmittance. In other words, all of this light is sensing, going, okay, this is making it all the way through. Calibrated at that, and then I said my absorptions at that point is going to be 0. Boom. So this was like the baseline deal. 100% transmittance, absorbance is 0. Then I took, I don't remember who was it. Was it yours, Alex, that I took? Then Alex brought his up, and we knew that was a 1 molar solution. And then I could adjust the machine that says, okay, based upon this being a set value of 1, this is what we're going to use as the standard. So the machine, Mr. Blaze, do you mind? So this is, so I calibrated and I said, okay, this is a 1 molar concentration. Okay, so when the machine says, okay, with this combination of transmittance and absorption, we're going to make this read 1.0. So this was the benchmark. So theoretically, and this is one of the questions, I think it's question number 4. Do not make question number 4 difficult. So it's on the back side, and I go, okay, if I set it as if I calibrate it as a 1 molar solution reading 1, then if I bring up a 0.5 molar solution, Mr. Taylor, what should the machine theoretically read?
0.5.
0.5. Don't make it difficult. Okay? If I calibrate it at 1 and you bring up a solution that has half the concentration, it should be reading 0.5. Okay? Don't make number 4 difficult. It is the easiest question I will ever ask you in this class. Don't add it, don't divide it. It's 0.5. If you brought up a 0.25 molar concentration, it should read 0.25. That's it. Boom. Okay? Now, on that experimental error, well actually let's look at the big picture. So when you look at your data, so here's your data table, right? Here's 1 molar, 0.5, and 0.25, right? First column was what, transmittance? Yeah. So when you look at your transmittance, okay? So Heather, like what was your transmittance on the 1 molar solution?
61.0.
61.0. Now, that's actually a percentage, okay? So what we're saying is that 61% of the light that we started with on one side of this solution made it through to the other side. So if there was like 100 of you, I send 100 of you down to the office, 61 of you make it. The other 39, bad day. Now, when you went to the 0.5, Heather, what was your transmittance?
71.8.
79.8, and then finally it was what?
It was 71.8.
Oh, 71.8?
Yeah.
Okay, and then what was the last one?
86.2.
86.2. So, as the concentration became less, what happened, or excuse me, as concentration became less, what happens to your transmittance? It goes up, right? Because more and more of that light is making it through because there's fewer and fewer particles to absorb that light, okay? Now, then you had absorbance. Now, absorbance is just a number, okay? There's no units with it. It's just a raw number. So, Heather, what was your trend as you went down? It decreased. So what you should see is that there's like an inverse relationship here. As your transmittance goes up because less and less and less and less and less of the light is being absorbed, so more and more and more of it makes it through. Okay? So that's why these are inverse relationships. So that's the type of question I'm going to ask you on the test. I'm going to say, okay, hey, you don't know what a concentration is, but you put it in the machine and you get a certain value. then if you dilute that solution, what should happen to the transmittance? Should it go up? Should it go down? What should happen? Okay. Now, then you had what the machine reads as the concentration. Most of these were pretty good. Some of them were a little bit off. So let's say on that 0.5, you brought it up. So Heather, what was your value for the 0.5 on the concentration?
0.87.
Okay. Oh, okay. How about someone who's a little bit closer? Yes?
0.98.
Huh?
0.98.
No, on the 0.5 one.
Oh, 0.57.
Okay, 0.57. Okay. It's going to be the same process, but this is going to look a little bit better. So this is your experimental value. You got 0.57. What theoretically it should have read 0.50. So to calculate that experimental error, you're going to take your theoretical, and that's the formula that's on the sheet. So you're going to take 0.50 minus 0.57, and then you're going to divide that by 0.50. This is like an absolute value, and then you're going to multiply by 100 to get it as a percentage. So this has no units. Experimental error has no units at all. Okay? There are no units because everything's going to cancel out. So it's just a percentage. So here's the deal. The closer this is to 0.5, the smaller the experimental error. If Heather got 0.87, that's going to be a pretty big experimental error because of the fact that she was relatively off by quite a bit. Maddie's isn't going to have as much experimental error because she was only off by 0.07. So experimental error is just an indication of how close you are to an accepted value. Okay? So it's always theoretical minus experimental over theoretical times 100. Always the same way every time. Then it's an absolute value. Boom. There you go. Cool with that? Got it. Good. All right. So then you're going to have the graph. So basically your transmittance, okay, is going to go from 0. I'd set up that transmittance because you want that on that x-axis. I'd just go from 0 up to 100. And then your absorbance is going to go somewhere between 0 and 1. So I just go 0 and then 1 and then spread this graph out as far as you can. You have an entire half sheet of graph paper. Don't make this graph like there, okay? You have a half sheet of graph paper. The tree has died. Have it not died in vain. Use the graph paper. You don't get bonus points for little postage-sized graphs. Bad. My eyes are getting bad as I get older. Okay. On number 1, so let me go kind of through these questions, because these are the kind of questions that you're going to have to be able to do on the test tomorrow. Okay, this is the situation. Okay, real life. Boom, here you go. So on number 1, you're trying to find the molarity. So let's talk about this number 1. You're trying to find the molarity. So at the end of the day, what two bits of information do you have to find the molarity of the solution? Moles and liters. You got to have the number of moles and you have to have the volume of liters. Okay, that's it. Those are the 2 bits of information that you have to have. Now, let's talk significant digits. You have 14.7. How many significant digits? 3. You have 380.0. How many significant digits? 4. So therefore, I have 3 and I have 4, so therefore my answer has to have how many significant digits? 3. Okay? Yes?
So, say you have 1.0 moles, but that's just an assumed value, right?
Oh, no, that's a measured value. So like on what are you talking about?
Okay.
On number 2?
It'd probably work better on number 4 on the bottom.
Okay.
So, don't you take the molarity, so 2.0s on the numerator, then you have 1.0 liters on the bottom, right?
Yeah, because that 2.0 molar solution means that you have 2 moles per 1 liter.
So the 1.0 liters doesn't affect the number of significant digits, or the...
Where are you getting 1.0 on number 4?
Because you take the 2.0 from the molarity.
Yeah.
And then you divide it by 1.0 liters.
Yeah, but it isn't like, it's per liter.
Okay, so
Okay.
it doesn't.
No, so what determines it is the 2.00. Okay? It's 2.00 moles per liter.
Okay, that makes sense.
Yeah, that one has nothing to, no, bad, no. Yeah. So that 2.00 is what determines that number of significant digits.
Okay.
Okay? So, anyway, on number one, and this is what you've got to be able to do. So there's a whole bunch of things that are going to get wrapped up into this final, or this test tomorrow. So first off, you got the 14.7 grams of aluminum phosphate. So what do you have to be able to do before you even start the problem? What do you have to figure out?
Formula.
Yeah, you got to figure out the formula of aluminum phosphate. If your formula for your aluminum phosphate is bad, everything else is just going to go south. So what's the formula for aluminum phosphate? AlPO4. Aluminum's 3 plus, phosphate's 3 minus, boom, it's just AlPO4. So if you don't get that right from the beginning, literally, everything else is screwed. So one of the things that I'm worried about is tomorrow. Like let's say, for example, you get on number 2. You got sodium chloride and you have magnesium chloride. And my concern is that you're just going to write, oh, magnesium chloride, and you're just going to put MgCl. Is the formula for magnesium chloride MgCl? Mr. Hill?
No,
Why?
because the oxidation numbers have to cancel out.
Beautiful. So what's the correct formula for magnesium chloride?
MgCl2.
MgCl2. So it's going to be the little things that are going to screw you over tomorrow on this test. So sodium chloride is NaCl because it's 1 and 1. But magnesium chloride is MgCl2. Okay? So pay attention to the little things. So anyway, so on number 1, if that goes well, your molarity should be between 0.3 and 0.5. Okay? On the bottom set of questions. Somewhere between 0.3 and 0.5. That should be your molarity. On number 2, when you're figuring out the grams, both of those grams should be between 10 and 30 grams. Okay? So the sodium chloride, boom, there you go. Now, here's what I want you to look at. When you look at number 2, you got a 1 molar solution of sodium chloride and a 1 molar solution of magnesium chloride. And you're going to make 0.25 liters of each. So here's the question, and this is what you've got to be able to articulate tomorrow. I have the exact same molarity. I have the exact same volume. Why are the masses different? Why is the mass of the sodium chloride less than the mass of magnesium chloride?
Molar mass.
Yeah, the molar mass of magnesium chloride is greater than the mass of molar mass of sodium chloride. Okay? So that's what you want to be able to look at. Now, let's talk about number 3. Which solution will contain more particles? Explain your answer. So there's 3 possible answers that you could have. Okay? So let's take a vote. Option number 1 is the sodium chloride is going to have the most number of particles. Option number 2, the magnesium chloride is going to have the most number of particles. Or option number 3, they're going to have the same number of particles because of the fact that it's the same molarity and everything's the same. So how many vote the sodium chloride is going to have the largest number of particles? How about the magnesium chloride? 1, 2, 3, 4. How many vote that's going to stay the same? Okay. So, Heather, why do you think it's going to stay the same?
Because it still has the same amount of moles. right?
Okay.
And it always has 6.02 times 10 to the 23.
Okay, and a mole of anything always contains the same number of particles.
Yeah.
And it's the same number of moles, everything should stay the same.
Yeah.
Okay. So Moses, why did you say that the MgCl2 is going to have more particles?
Because if you're taking the NaCl and you have less amount of grams that are going into it, and you have the magnesium chloride, that has more grams going into the solution than it should weigh. Right?
I'm not asking about what it weighs. I'm asking which one's going to have more particles.
Kind of the same thing.
No. No,
'Cause if you
it's
have
not.
If you have more mass, doesn't that have more particles?
Okay, let's say that I have one bowling ball and I have 10 ping pong balls.
Okay.
So bowling ball is going to have more mass than the 10 ping pong balls, right? But if I have 10 bowling balls and I have 10 ping pong balls, they have the same number of particles. Okay, so I'm asking about the number of particles, I'm not asking about the mass. Mr. Taylor,
Can I change my answer?
to what?
They're the same.
Okay, so you want to change it to the same. Why do you want to change it to the same?
Because like you said with the bowling balls and the ping pong balls, they have the same amount of particles, but with
Okay.
different mass.
Okay? So does everybody agree that it's the same?
I still have confidence in my
Yeah, I
answer.
got confidence.
For some reason.
For some reason.
Yeah.
Okay. So let's talk sack lunches. Okay? We're going to answer this in terms of sack lunches. So let's say that you want to make a cheese sandwich. Okay? You're going to make a cheese sandwich. And the cheese sandwich, we're kind of, low on funds. It's the end of the month. Okay? So my cheese sandwich is going to consist of one slice of cheese and one slice of bread. Okay? So, hey, look, my story. Okay? So the formula is going to be CB. I have one slice of cheese, I have one slice of bread. Okay? Now, so in my sack lunch, I'm going to have 5 of these sandwiches. Okay? And they're all going to be stacked up nicely. Okay? Right? So in this, I have 5 sandwiches. So the concentration of this is 5 sandwiches, 5 CBs per lunch bag. Okay, so that's my concentration, right? They're all stacked up nicely. However, in the course of the day and being jostled around, right, we're going to take the bag and we're going to shake it up. Okay? So what's going to happen to the cheese and the bread?
It's going to spread out.
It's going to spread apart. They're going to become what we call disassociated. It's like it's going to dissolve. They're still going to be in the sandwich, but they're going to dissolve. So once the sandwiches dissolve, so I had 5 of these. So I had 5 sandwiches, 5 CBs. But when it dissolves, what am I going to end up with? How many slices of cheese am I going to have? 5. How many slices of bread am I going to have? 5. Okay, that's cool, right? So what's the total number of particles inside the bag? 10, right? Okay. Now, Mom and Dad won the lottery. Wow, now we can make real cheese sandwiches. Okay? So now we're going to have 2 slices of bread, okay, with 1 slice of cheese. So there's another slice of bread. Okay? So imagine that here. Let's do a cross section. So 2 slices of bread, 1 slice of cheese. So now what's the formula for the cheese sandwich? C B2, right? So again, in the bag, we're going to start off with 5 sandwiches. Okay? Same number of sandwiches, right? Now we're going to jostle it around. Now what's going to happen?
5.
We're going to get 5 slices of cheese.
10 slices.
Oh, 10 slices of bread. Right? True? So now what's the total number of particles inside the 15? So now I have 15 particles per bag. So we had NaCl. You think sodium chloride dissolves in water?
Yeah.
Yeah, otherwise we wouldn't use it in soups. Okay, kind of dissolves in water, it's kind of a thing, right? So this is what we say that it's soluble, it dissolves. So that breaks up into sodium ions and chloride ions, right? So if I have 1,000 sodium chloride particles, how many sodium ions do I get? 1,000. How many chloride ions do I get? 1,000. What's the formula for magnesium chloride? MgCl2. So that breaks up into what?
Magnesium.
Magnesium ions and what?
Chloride.
How many chlorides?
2.
2 chloride ions.
Am I right?
Yeah, you're right. Your rationale was completely wrong, but you were right. So look, if I have 1,000 particles of these, how many particles of magnesium do I end up with?
2,000.
1,000? But how many chloride ions do I get?
2,000.
2,000. So I actually have more particles of magnesium chloride when it dissolves. Don't get cocky.
No, he looked over at me and he said, "You're dumb." When
I never said that.
Yeah,
you
I'm just
did.
putting it back on.
Okay, you were right, but your rationale was wrong. Okay, Heather had a decent rationale, and she would have been right if everything had ionized in a 1-to-1 ratio. But because this becomes twice, you get more particles out of this because it's MgCl2. Now, what if it had been aluminum chloride and it had been AlCl3? How many chloride ions would you get out of that? 3. So that would be a lot more particles. Okay? So, cool with this. All right. It was just kind of to make you think a little bit. Okay. Any other questions on the lab? We're good? If you want to hold on to this lab and use it to study and hand it in tomorrow, that's fine. If you're done with it and you're feeling good about it and want to hand it in, I'll have it graded before tomorrow morning. And you can come in before school if you want to get it then. But it doesn't make me any difference. Hand it in, don't hand it in. Just as long as I get it tomorrow, okay? It isn't like you don't have to hand it in. You just can hold on to it till tomorrow. Okay, John, stop that for a second.